Hello guys and welcome to my YouTube channel. In this video I'm going to explain BJT transistors and their use cases. An NPN transistor has three semiconductor regions: an N-type collector, a P-type base, and an N-type emitter. The emitter is heavily doped because it injects many electrons. The base is very thin and lightly doped, so only a small number of electrons recombine there. The collector is larger because it collects carriers and handles more heat. This structure creates two PN junctions, the base-emitter junction and the base-collector junction. In an NPN transistor, electrons flow from emitter through the thin base and into the collector. This is why a small base current can control a much larger collector current. A BJT has three terminals: base, collector, and emitter. For the NPN symbol, the emitter arrow points out. For the PNP symbol, the emitter arrow points in. Inside the transistor, there are two PN junctions, the base-emitter junction and the base-collector junction. The diode model helps us understand the junctions, but a real BJT is not simply two separate diodes. The thin base region is what makes transistor action possible. The key current equation is emitter current equals collector current plus base current. This is the foundation of BJT operation. For an NPN transistor, the emitter arrow points outward. NPN transistors are commonly used as low-side switches, where the transistor connects the load to ground. An NPN turns on when the base is about 0.7 volts higher than the emitter. For a PNP transistor, the emitter arrow points inward. PNP transistors are commonly used as high-side switches, where the transistor controls power from the positive supply. A PNP turns on when the base is about 0.7 volts lower than the emitter. Simple rule: NPN arrow points out, PNP arrow points in. Biasing means setting the correct DC operating point of the transistor. This point is called the Q point. The first circuit is fixed bias. It is simple, but it has poor stability. The second is collector feedback bias. It uses negative feedback from the collector to the base, which improves stability. The third is voltage divider bias with an emitter resistor. This is the most common and stable method. Good biasing is very important, especially in amplifier circuits, because it keeps the transistor in the correct operating region. Here we have four BJT operating regions. In cutoff, both junctions are reverse biased. The transistor is off and collector current is almost zero. In forward active mode, the base-emitter junction is forward biased, and the base-collector junction is reverse biased. This is the amplifier region. In saturation, both junctions are forward biased. The transistor is fully on and works like a closed switch. Reverse active mode has the opposite biasing, but it is rarely used because the gain is low. Remember, cutoff is off, saturation is on, and active mode is for amplification. The circuit shown is a common emitter amplifier. The input signal enters through the input capacitor, and the output signal is taken from the collector. For amplification, the transistor must operate in the forward active region. That means the base-emitter junction is forward biased, and the base-collector junction is reverse biased. A small change in base current creates a larger change in collector current. The output signal becomes larger than the input, but it is inverted by 180 degrees. This is a key feature of the common emitter amplifier. NP and BJT can be used as a low-side switch. The load is connected to the positive supply and the transistor connects the load to ground. When the input is low, there is almost no base current. The transistor is in cutoff and the load is off. When the input is high, base current flows. The transistor enters saturation. Collector current flows, and the load turns on. So for switching, cutoff means off, and saturation means on. For inductive loads like relays or motors, always use a flyback diode to protect the transistor. Here we have the forward active operation of an NPN transistor. In active mode, the base-emitter junction is forward biased, while the base-collector junction is reverse biased. For a silicon transistor, the base-emitter voltage is usually around 0.7 volts when conducting. The collector voltage is higher than the base voltage, and the base voltage is higher than the emitter voltage. In this region, a small base current controls a larger collector current. The emitter current equals collector current plus base current. Forward active mode is mainly used for amplification. Thanks for watching this video, guys. Please don't forget to like, share and comment below. Also subscribe to my YouTube channel for more videos.